Hello everybody, this is 4.5, which is optimization 2, and this will complete chapter 4. And in this optimization 2, we solve some applications in which we use 4.4 as well. So the guidelines is to assign the letter for what's mentioned, and of course to draw a sketch to make it helpful if possible to solve and to solve. Find an expression to be optimized. You may run into two equations or something like that, but there is one that you need to maximize or minimize. Use the conditions. Of course, there may be some constraint there. So for example, weight has to be certain thing, so it does not come up to be negative. And we optimize based on what we did in 4.4, maximize or minimize. Let's look at this traditional example. Find the dimension um, of a rectangle here. So rectangle, let's say give it this width and this length. And it says here the perimeter, which is 2x and 2y is 120, has the largest area. So the area is the one that is maximized. And since it's the one that is maximized, so we're going to focus on its equation, but we want a single variable. We don't want x and y. We want one of them. So let's get y from the perimeter equation, right? So 2x plus 2y equal 120. 2y is 120 minus 2x. So y divided by 2 on both sides, you get 60 minus x. So the constraints we talk about here, y has to be positive, right? So 60 minus x has to be positive. Um, so x has to be less than 60 for sure. So if you run into different solutions and you need to pick, you will pick a number that is less than 60. This is just to show how you think about the conditions. So now in A, substitute this, and you get A equal x times 60 minus x for y, which means A is 60x minus x squared. And just like we did in 4.4, to find that absolute max, or to maximize, we need to find a critical point by doing the derivative. So 60 minus 2x, and we set it to 0, and we find x equal 30. And it is less than 60, so that's definitely a solution. And x here is the shortest, right, side. So if we want the y side, let's which is based on this, not as we started solving this, based on the rectangle idea. Y is 60 minus 30. So in this case, they end up being both the same. So this rectangle under these conditions turns to a square form. In order to have 120 perimeter and the largest area, this rectangle turns into a square. Let's look at another example. We have an owner here that wants to fence this with 3012 yards fencing. And as you see, there are three sides to fence. And if we call this X and X, this is going to be Y. So based on this, X and Y is going to be the amount of fencing that is available. So 2x plus y equal 3012. But the purpose as well is to maximize the largest area. So to maximize the area, so similarly the area is x times y. So this is to maximize. Therefore, we need the y to be switched in form of x. So from the fencing, we solve for y, and we get 3012 minus 2x. So use in A, instead y, we have 3012 minus 2x. And that's gonna make 3012x minus 2x squared. So that's the area formula. Similarly, similar to the first example, 3012 minus 2x has to be non-negative. So let's differentiate. And we get 3012 minus a 4x. And set to 0, we get x equal 753 yards. All right, so this will make the shorter side. So the longer side, or the y side, is a 2x will be 753, and that's gonna give us 1506 yards. You see, so this one, it's a similar situation of a rectangle, but to fence the three sides and have a maximum area, it only happens when x is 753 and the y is 1506. So here, if somebody asks what is the maximum area, then we need to go to the formula this one here, 3012x minus 2x squared, and x is the shorter one, the 753. And that's going to lead to 1,134,018 yards square. Okay, so let's say another example, and this problem talks about there is this area here, this place here that's of interest. It's made by wood and steel from one side and wood on the other side. And the two sides will be constructed with pine boards, and the fourth side will be made by the galvanized steel. If the pine board fencing costs $5 running foot, and the steel fencing costs $2 running foot. determine the dimensions of the enclosed. So the graph is okay. You can write on it, or you can switch it to say, okay, this side here is this one, and you have something like this. So of course this is the wood, and this is the wood, and this is the steel, and you can call this X and this is Y, and of course also this will be X. And okay, so if we switch it to this sketch to make it simple, and minimum cost, so we're minimizing. So let's read the whole thing here. Determine the dimension of the enclosed that can be erected here at minimum cost. Round your answer to 1 decimal place. So the area here is, you see, the store decided to enclose an area of 809. So that's what's given. The X times Y in this form of shape, let's say rectangle, square, but this shape, the area, you find it by doing X times Y, you get 809. So what is it available here? The costs. The cost for the wood, you have two X's there, two sides, times the $5 per foot, right? So X and X. And for the steel, it's 2 times Y, right? So that's that. So this is a 10X plus a 2Y, the cost. We're minimizing the cost, so we're going to focus on the cost. And same thing again, we have a Y, so we'll go back to this and get the Y from it. So C is a 10X plus a 2, 809 over X. So C is 10X, multiply the 2. So now, so next is the derivative, so it's 10. Then you can do the quotient rule or reciprocal rule, and that's going to switch this to, so you can try it for this part, and you get 1619 over X squared. We need to check C prime equals 0. So that means 10 minus 16 over 19x squared equals 0. So like the 4.4 example, you set it, and that's a 10x squared, 1619. So is 1.9, and x is, but remember the restrictions talk about here, x is a dimension, it cannot be negative, so x is going to be taken as a square root of 161.9, and which going to be x in this case to a decimal. Here the instructions round to your answer to 1 decimal. So that's a rounding there. So now the important part that you need to do the y. So let's put a note. Use kind of we should say maybe the exact value of x to find y. This way, so you don't have um, a computation error, because if you use 12.7 is rounded, and x equal 161.9, that's kind of exact, and x equal 12.7 is it's a rounded, which means it's an approximated number, not exactly like the other one. So if you do that, you will avoid running into computation error. And in this case, you'll have y equal. So we had 809 divided by a square root of 161.9. And let's try it. This should be 63.56, and rounded to that will give us this, to 1 decimal place. So these are the important things to think about as you're doing these problems, so you don't run into errors. So let's see this number 4. By cutting, this is another traditional problem that's usually done in optimization. So by cutting away identical squares from each corner of a rectangular piece of a cardboard. So maybe you want to think about, you have a cardboard like this one. And you're going to cut these pieces here. So you can fold them and make the box, right? And if the cardboard is 21 inch long, so 21 inch long, which means from here to here is 21, and from here to here is 5, and that will find the dimensions of the box that will yield to the maximum volume. So we're going to cut an X amount, which is the same, of course. If you do X here, that's X there, X here, X, X. It's going to be the same thing, such that when you fold this to have a box, let's draw a box here. And of course, the inside is going to be something like such that when you fold this box, you're going to have the maximum volume. So what does this mean? If this is X and this is X, and this width is 5, that means this remaining part here, let's do a different color here. It's 5 minus 2x. If this whole thing is 21, and this is x, and this is x. So what's left here is 21 minus 2x. So when you fold this box here is 5 minus 2x for the width and 21 minus 2x for the length. That's how it's going to end up, right? So, and the volume is going to be, of course, this side here is x. That's the when you fold it. So the volume is going to be that 5. I need a little more space. 5 minus 2x, the width, times the length, times the height. So so multiply all these. Maybe pause the video and multiply so you check. You should get 4x cubed minus 52 x squared plus 105x. And you know that we need to find v prime after that, which is going to be 12 x squared, 104x, and 105. And let it equal to 0 to see if we're going to find that number there. And so need use quadratic formula to find for this v prime, just like a quadratic equation, you use quadratic formula on it, and you will get x equal 7/6 and x equal 15/2. So now we have 2 dimensions which one to pick. The other ones are easy because one is positive, one is negative. We can use the negative and that. So let's see what's going on here. So when we want to build this, so now we talk about that part. Maybe let's do this one in view. You see this side of 5 minus 2x? This side, of course, cannot end up being negative, right? So, which means 5 greater than 2x, which is x is less than 5/2. So that's one restriction for the x. It has to be less than 5/2, which is 2.5. And when we look at the other one, 15, this one, that's a 7.5. And when we look at this one, it's a 7, which is about 1 point, let's say 1.7. So here, x is less than 2.5. So from the note, x must be less than 2.5. So we take x is 7/6 and reject x as 15/2. So that's how you decide when it's not easy to decide, if like the negative and positive. All right, so once we pick this, of course, let's add it to the note here. X must be, of course, greater than 0. Must be greater than 0. Of course, otherwise you won't exist. then 0. So x. So if we want to put all together, it's something like this. So now what we're going to do, we're going to investigate. We have a few points. We have the 5/2. So we have the 7/6. We have 0, and we have 5/2, which means x, right? We say is between 0 and 5/2, 2.5, and the 7/6. So what's going on here? We're going to, if you investigate, you're going to find out. So let's use the function here, v. So if you try in v, we can call it vx because it's a function depending on x, 4x cubed minus 52x squared plus 105x. If you try 0, you get 0. If you try 7/6 and keep, of course, the fractions just like the examples, you get this. And if you try 5/2, you get 0. So definitely the answer is this one. Definitely this is where the maximum is happening, right? So that's where the maximum is happening. If the maximum is happening there, now we can build the box. So now we can return and say, this is 7/6, this is 7/6, and this is 7/6, right? The only thing here, note again, not to run into computation error. So note, build box using 7/6, not the rounding, to avoid errors, right? And if you do that, so the first x with 7/6 is going to be for us with the request to round is this, but we're not going to use 1.17 into these other here, 5 minus 2x and 21 minus 2x. We're going to use 7/6. So the other dimension is 5 minus 2 times 7/6, and that's going to be 2.67 inch. And the next dimension is the 21 minus 276 is going to be 18.67 inch. Another example, this company uses aluminum container that have the form of a right circular cylinder, so that should stand for a cylinder that has, you know, with the two right, and it has these circular tops here. So that form right circular cylinders find the radius and the height of a container. So if this is R, then the area at the bottom is 2 pi R, and if this is the height, then that's the height, and H capacity is 44 inch, so that means the volume is 44 inch cubed, and it's constructed using the least amount of metal. So least amount of metal, that's a surface, right? That's the surface area. So we need to find the surface area for this right cylinder, and that's going to be a 2, the bottom and the top, 2 pi r squared, and same thing, this one is 2 pi r squared plus 2 pi r times h. 2 pi r, that's that's for the circumference. If you open a circle, if you have a circle and you open it, that's going to be the circumference of the circle. So that's where 2 pi r come from. This is a 2 pi r. And if you take this and you open it, that's a 2 pi r. And of course, you multiply it by the h, because this side, maybe we can do, this is a nice way of showing it. You have the top, the bottom, and if you cut the cylinder and you open it, it's going to look like a rectangle. So that's a 2 pi r, and this is h, and this is another 2 pi r. So that's how the surface area is built, and also it's a common, maybe a formula that that's available out there. A surface, we can rename this S, and now we are interested in this. So R, of course, is not going to be negative, that's for sure. And what else we need? The volume is, we know the formula for the volume is going to be that base pi r squared times the h, this area times the height, that's going to be the volume. So we're interested to minimize this one. So we won't keep it, usually we do x and y, so we just use 1 in it like x. Here we have r and h, so we just use the r, which means from v. Let's get the h, pi r square h. H is going to be v over pi r square, and use it in S that we need to minimize. So H is going to be v over pi r squared, so 1 r is going to cancel and pi is going to cancel, so 2 pi r squared plus 2v over r. Then you know the drill. Now after this, you do S prime, the first derivative. Set it to 0, so let's just go ahead and do it here. With respect to r, of course. With respect to r. Maybe we should do it this way, correct way. With respect to r, so you get 4 pi r minus 188 over r squared. Of course, you do the quotient rule on this, or reciprocal rule. Quotient or reciprocal rule. I think I should instead keeping V, let's just change it with 44 because it's a 44. Yeah. So here this is a 44. So this is a 44 over pi r square. So here it's a 44. I did it and then multiplied. So this is going to be not 188, it's just 88. Okay. Because I was multiplying it and thinking about it as 188, then I see that it's it's a 44. So V is 44, so H is 44 over pi r square. We put that for H. We put that for H. Then, right. Not needs to make it clear. It's H. All right. Then we get the 88. So the derivative is, we have the 88 there. So let's change this one to 88. And we do the power rule that gives us 4 pi r, and we do the quotient reciprocal rule on that one. We get negative 88 over r squared. And you know, now next is s prime equal to 0. So 4 pi r minus 88 over r squared equals 0. So we get 22 over pi. So r is a cube root of 22 over, yeah. So this is kind of the exact value that we need to use, right? Because the answer, we use a calculator on this one, and for the rounding that is asked for the problem, we can use 1.91. However, for the height, we're going to use the exact value so we don't run into errors in computation. So and that's going to be 3.83 inch, right? So as you see a summary for all these, there is no problem almost that is same. However, the guidelines or the procedure is same. So the difficulty is going to be in the setup and sketching. Once you sketch it and you set it up based on what it is asked, from there it's just the same process again and again. It's not going to be a problem. So I would recommend to practice some of these. I will do a few more, of course, in class, and we'll combine them. So we'll cover all this homework between this and the examples in class, and that will cover this homework, and you see different ways of working these. So you can see that after the sketch, whatever is given gives you some type of formula or equation. And based on that, you will get one of the variables. You have a formula or equation for whatever it's maximized or minimized. you substitute. So you have only one variable. So A in terms of X, not in terms of X and Y. You see, you have X and Y just in terms of X. Then we solve. Once we substitute, we get the equation for whatever we're maximizing or minimizing, take derivative equal to 0, and solve. In some occasions, you're getting directly the answers, right? And in some occasions, like here, we're getting 2 answers, but we reject negative because X cannot be negative, right? So we use the positive one and use its exact value to find the Y. And similarly for these traditional box example, but here based on how it's built, it builds in it a restriction for X. And that restriction for X is the one that decides when you have to pick 2, right? There was this answer and this answer, but we picked that one based on that note and restriction. And of course, you have another example where you have now a surface area that you want to build something with, and minimize that surface area in order to still have the same volume that you wanted, let's say, for a can or something. So, and you'll see how companies, of course, deal with this stuff and how they improve their products and containers and like the idea of recycling to use the least amount of material for the same product. And we'll solve more examples in class, and they're going to run in similar things. So just how to set up, and once they're set up, they're going to be solved the same way. Thank you.